Our next lesson will cover the six basic types of machines. I have them listed here for you with a brief description, and then on the next couple of slides I have some pictures. You will need to memorize all six types of these machines. The first one is a lever, and that's very similar to a seesaw. Next, we have an inclined plane, and this would be used for maybe to lower an object gently or to lift something that's too heavy to physically lift. If you think about like on the back of a moving van, they use that ramp to lift objects up into the truck. Third, we have a pulley. And usually a pulley is used to change the direction of a force, but not necessarily the amount unless you're using multiple pulleys. And we're actually going to have a lab about that so you can see the difference between using one pulley versus several. Fourth, we have a wheel and axle. This simple machine is two different size rotating shafts that's fixed to the same rotating system. So think about the wheels of a car that are connected by an axle between them. Fifth, we have a screw. And a screw is something that would have a huge squeezing force. And actually, they were used in ancient times for torture devices. If you've ever heard the term thumb screw, that would be an example. And then lastly, we have a wedge. And I mentioned pushing down to get a tremendous force sideways. This would be, for example, the blade of an axe. So it moves downward, and then the thing that you're splitting, maybe a block of wood, would be moving over to the side. Now, each of these machines have more applications than the ones I talked about, but that's just to get you started. So let's look at some pictures. So this slide gives you a picture of each simple machine and then shows you an application. So take some time and look through those. Feel free to pause the video if you wanted to make note of any of them. And on this slide, hopefully you can recognize each of the different types of machines. So in this picture, we have a lever. This one is using a wheel and axle. This obviously would be a screw. The axe would be a wedge. Here we have a pulley. That one's really easy to recognize. And this one actually has two. We've got the wheel and axle on the wheelchair, and we have the inclined plane for the ramp. Now we're going to break down our machines into mechanical advantage and ideal mechanical advantage. So we're going to talk about the forces and then the distances that objects move when using these machines. So I picked a lever or a seesaw for this first one. So if you consider an object sitting on the edge of a seesaw and then you were to push down on this side, then your object would lift on the other side. So for right now, we're just looking at the types of forces that you're going to see in simple machines. We are going to use subscripts to denote the different types of forces. If there's an E, this is the effort force, and this would be what the person does in a word problem. So anytime you see a person applying a force, it's going to be labeled the effort force. The resistance force is what you're working against. It's resisting being moved, and typically this would be the weight of your object. And remember that sometimes you are given the mass, so in order to calculate the weight, you would need to multiply the mass in kilograms times 9.8. Next, we're going to look at a bottle opener. So I've drawn part of a bottle of your favorite non-alcoholic beverage, and then we're going to look at the opener to lift off that bottle cap. Now, if you were to try to lift that cap off right here, that would require a tremendous amount of force, but if we use the bottle opener and we apply a force a certain distance away from the actual object itself, it's going to seem a lot easier. So if we were to look at forces, the resistance force would be the one where the bottle cap is, and the effort force would be where the person applies a force to the handle. Now let's say we've pried that bottle cap open just a little bit. So now that we've opened the bottle, let's look at the distance that each section moves. So first, we're going to look at the resistance distance. I know that's a bit of a mouthful, but that would be how far the object actually lifts. And then if you think about where the handle started before we opened the bottle, and we had to move that handle a much larger distance, this is what we call the effort distance. So it gets an E for a subscript for effort, and that again goes with the person, and then the R is for resistance, and that would refer to the object moving. Next, we're going to use these forces and distances to come up with some equations for our mechanical and ideal mechanical advantage. Mechanical advantage would be the ratio of the resistance force over the effort force. And so I have an example problem for you. If a bottle of root beer requires 300 newtons of force to remove the cap, but with the opener, which the person is applying the force to, only 45 newtons of force are needed. So this mechanical advantage would be 300 newtons over 45 newtons, which gives us a mechanical advantage of approximately 6.7. Notice that the units cancel out, so there are no units for mechanical advantage. And what this number does is it tells us how many times the simple machine multiplies our force. So by using the bottle opener, we're getting nearly 7 times as much force out of the bottle opener as what we need to apply. Similarly, ideal mechanical advantage is also a ratio, but I want you to notice that the effort and the resistance switch places. So when we look at our ratio of distances, this time it's the effort on top and the resistance in the denominator. So again, I have an example problem. The ideal mechanical advantage would be a ratio of our distances. So the crowbar, which the person is using to apply, would be 0.75 meters. And then the lid, however, which is our object, would only move 10 centimeters. Notice that it is centimeters, so we will need to convert when we plug in. And this is going to give us an effort distance of 0.75 meters in the numerator and a resistance distance of 0.10 meters in the denominator. Again, the units cancel out, and this particular machine gives us an ideal mechanical advantage of 7.5. The equations really are that simple. If you get confused on which effort or resistance to put in the numerator, an ideal mechanical advantage and mechanical advantage are typically going to be larger than 1, so you would want the larger number to be on top for both of these equations. Next, we're going to talk about if a machine is ideal. When you see this word ideal, all that means is that there's no friction. And in the last chapter, we talked about work, which would be force times displacement. In this particular instance, our displacement and distances are going to be the same, so I'll probably interchange those scalar and vector quantities, and to make things simpler, I'll just be saying force times distance. So if our machine is ideal and it has no friction, that means that we are going to get out whatever work we put into the object. So when we talk about the work that goes in and the work that goes out, these are the quantities that we will be multiplying. For the work out, that would refer to the object, so you can think out and object. And then in would be what the person is applying. You can think that the person puts in the effort. So we would multiply the effort force and the effort distance for the work in, because the person puts in the effort. And then the work that you're getting out comes from the object, and that would be the resistance that you're working against, and that would be the resistance force times the resistance distance. And then just as a side note, we could rearrange those. I basically uncross multiplied. So if our machine is ideal and the work values are equal to each other, the MA and the IMA are also going to be equal to each other. What I put in the box right here, you would need to know how to find work out and how to find work in. So make sure you take note of those equations as well. The last of the equations that we're going to do about machines before I give you some example problems will be efficiency. So if a machine is not ideal or it's not perfect and we do have friction, we can figure out how efficient that machine is. And I forgot to take off spell check, so just ignore the red squiggly. But to find the efficiency of a machine, you simply take the work out over the work in and you multiply by 100. And this will give us a percentage on how efficient the machine is. If you did happen to have an ideal machine and we looked at the ratio of work out and work in, if the machine were ideal, those two things would be equal to each other, and this would give us a ratio of 1, which would in turn let us know that the efficiency of that machine is 100%. So remember, that's only true if the machine is ideal, which means there is no friction at all. You will not see over 100%, so if that happens, you probably switched the order that you were dividing your work values, so nothing over 100%. We can also calculate efficiency in terms of mechanical and ideal mechanical advantage, and this would be the equation for that. Now we're going to do some example problems. For all of our examples, we want to identify 4 things. We want a resistance force, an effort force, a resistance distance, and an effort distance. So those are the 4 things you're going to look for anytime you see a word problem with machines. So Olivia is going to use a pulley system to lift a 24 kilogram box. Notice that that's kilograms. That is referring to the object. That will refer to our resistance force, but we need to convert kilograms to newtons. So let's do that real quickly. You should get 235.2 newtons. The box, it's still the object, is moving a distance of 16.5. So since it's referring to the object, that will be the resistance distance. So we're going to plug that number in. Now we see that Olivia, the person, is exerting a force of 129. So the person puts in the effort. So the effort force will be 129 newtons. And the person needs to pull the rope 33 meters. So we have some sort of system of multiple pulleys. Now that we have our variables all identified and numbers assigned to each one, we can calculate what's asked for. So first we need to find mechanical advantage. I'm going to block out the screen so I can start with a clean slate. So let's erase. Mechanical advantage is our ratio of forces. So resistance over effort, or F over phi. You should get about 1.82. Let me go back and write those numbers in for you. Okay, next we have the ideal mechanical advantage, which is a ratio of our distances. Remember the effort and the resistance swap, so now we have D over dir, effort over resistance. The units cancel again, and you should get an ideal mechanical advantage of 2. Remember on both of these that your mechanical advantage and the IMA should both be larger than 1. So that's a quick way to check and make sure you put the numbers in the right spot. Now we're going to look at the efficiency. We had 2 equations for efficiency. One of them used MA and IMA. So since that's what we calculated, I'm going to go ahead and plug those in. And you should get approximately 91%. I would say this is almost foolproof because you cannot have over 100%. So if you forget which order to divide the MA and the IMA, once you divided and multiplied by 100, you're not going to have over 100%. So that's an easy way to remember which number goes where. For this example problem, I'm going to get you set up on identifying the variables, and then you solve the problem and come back and check your answer. To help you, I made a chart. The person puts in the effort, so that'll be FE and DE, and then the object is what you're working against. That's the resistance, so that's our FR and DR. In reading through the problem, you should have seen that Hannah, the person, exerts a force of 225 newtons and moves her into the lever 0.81, and then the object was already in newtons. You didn't have to convert mass to weight or anything like that. And then the object itself moved a distance of 13 centimeters, so we did convert that to meters. The work out, remember out is the object, would be FRDR, so I plugged those in, and you should get 162.5. We are multiplying our units of newtons times meters and coming up with joules, which is the unit we used for work in the last chapter. And remember, the person puts in the effort, so we're going to multiply FE and DE together, and you should get 182.25. And lastly, we're looking for the efficiency, so we simply look at a ratio of work out to work in and then multiply by 100. And you should get approximately 89%. This section letting you know that all simple machines can fit into two categories. I'm going to show you examples of each of these in class. You do not have to memorize which machines go into which categories. It's just a way to help you remember all 6 of them. So again, we will talk about this in class. And then lastly, you need to know that a compound machine would be 2 or more simple machines linked together. And I gave you some examples. And then next time in class, we are going to have story time. So I'm going to read you a story. And I'm also going to show you some really cool videos with some Rube Goldberg machines. Thank you for listening. Good luck.